Want to welcome you to my lecture today. Of course, today I'm going to walk us through the same material that we used on Monday. What I'm going to do today is summarizing uh, the total probability formula and the Bayes rule. I'm going to make use of the board. I'm going to summarize that. There's going to be application of total probability and Bayes rule in court of law. I'm going to walk you through that today, and in medical diagnosis. But let me just tell you in general, Bayes rule and total probability can be applied in virtually all areas. So I want you to sit down, just focus on the way I'm actually going to be doing it. Let me just tell you this. You cannot separate total probability, like total probability law, from Bayes rule. Okay, when you're applying Bayes rule, the denominator of the Bayes rule is the total probability. Okay, so I'm going to walk you through all of that today. So I'm still using the same material as the last one. Okay, now four of us want to demonstrate the total probability law, and I'm also going to demonstrate the Bayes rule, and I'm going to start from example. Let's take a look at this. We are in the court of law now. Okay? Okay? I want to start from jury trial example. Okay? And I want you to focus. Okay? Please be focused. Okay, now, every jury trial actually begins with the assessment of the probability of guilt of the accused, okay? Which means they actually going to have the probability that accused is guilty even prior to the presentation of evidence. So if I let G, okay, G, okay, guilty, okay, then I'm going to write, because there's going to be two states of nature here. It's either the accused is guilty or is innocent. Okay, now this is a complement of that. I'm actually going to write this innocent. Okay, this is G. Okay, the state of nature, the sample space partition into this. But the court is going to start with the probability of accused guilty. You can see this is unconditional probability. Okay, this is not conditioned on evidence because the prosecutor has not presented evidence. Okay, so this is probability of guilt. Okay, now if this is probability of guilt, okay, I want to believe what the Bayes theorem is actually talking about is the probability that accused is guilty given evidence. So right now, I'm going to call my E. E is evidence. Okay? So if I want to write the Bayes rule now, take a look at that. The probability, okay, somebody has been found guilty given evidence, okay, that is going to be equal, okay, you're going to switch this, the probability of evidence given guilty, the probability of guilty divided by the probability of the evidence. If you take a look at what I have here, okay, I called this guy posterior the other time. Okay, this is posterior. Okay, now this is likelihood. Okay, this is prior. Okay, and this is marginalization. Now I'm going to tell you, if you take a look at what I have here, if I want to generalize, Okay? Then I'm going to write the probability of belief given data equal the probability of data given belief, okay, multiplied by probability of belief divided by probability of data. Take a look at that generalization. Now, I'm going to tell you this. Reverend Thomas Bayes, 1759, actually made us to realize if we want to have an accurate prediction of the future events, then we need to be able to combine belief and data. Okay? Because no matter what, even before evidence, our mind can never be empty. We're going to believe on something, right? What we believe on may be true or not. So, and that is why what Reverend Thomas Bayes 1759 presented is we want to update our belief with data. I'm going to say that again. Updating our belief with data. Data is going to be evidence. Data is acting, is standing for evidence. Okay? It is not the other way around. It is updating what we believe with evidence. Evidence is going to be called new information. Okay? If you take a look at this now, this is the probability of data given belief. Of course, at the crime scene, okay, when the forensic analysis is done, of course, they're going to find a blood sample that match that of the accused. That is going to be the probability of data given belief. Okay, then what is the probability of belief? The probability of belief here is a prior probability. What do I mean by prior probability? A probability of the state of nature even before collecting data. Because they're always going to have something in mind. Now, when you take a look at this guy here, the probability of E, okay, is going to be called a total probability. If I want to rewrite that, I'm just going to write the probability of G given this is equal to the probability of this given this multiplied by the probability of G divided by. Now, if you take a look at this, it's going to be part of this. Okay, so I'm going to write the probability of this given this multiplied by probability of this. Then what is the other state of nature? Don't forget, the sample space is partitioned into guilty and innocence. So I'm also going to have the probability of A given this, the probability of this. Now, what am I talking about? This guy here, okay, is actually the probability of the evidence. Now, let me tell you this. Evidence can be found given that the accused is guilty, or evidence can be found given that the accused is innocent. Does that make sense now? So this is Bayes' theorem. Okay, and this guy actually becomes what I call the total probability. I told you the other time, the total probability is going to be a denominator for the Bayes' theorem. Go ahead.
What exactly does it mean, like, conceptually, the probability of evidence?
Okay, the probability of getting evidence is just like, the world is going to get evidence, right? And it's going to be under probability, okay? Even though it may take them forever to get evidence, but one way or the other, they're going to get evidence. So we're going to say the probability of the evidence is more or less like chance of getting evidence. Now, what I'm trying to say here, okay? Now they accuse this person, right? Now this person may be innocent or guilty, okay? Now when they accuse this person, this guy is trying to tell you that given the looking at the evidence, this is a probability that this guy can be guilty, or there's another state of nature that they can find evidence and somebody they accuse is not guilty. Can you see that? So which means the population of interest is more or less partitioned into this guy and somebody else in the same population. And that is why the sample space is going to have this guy and this guy. somebody is going to be found guilty or not. Does that make sense? Okay. Now, I want to go into, this is the application in law. Okay. I want to tell you, celebrated case of O.J. Simpson, 1993-94 in the state of California. They used a Bayes rule to decide the case. Okay. Now, I'm going to, so take a look at that. If you take a look at all this, A and B, you can decide, yeah, I'm using G and E. All what you just need to do, you need to, before you write your formula, you need to first of all start by what does this represent? Does that make sense? It is not compulsory that you have to use A and B all the time. Does that make sense? You can use whatever. Okay? Now, I will quickly take you to, we want to leave court now. We want to go into, let me see, there's one example under medical diagnosis here. Give me 1 second. Okay, let's come to medicine now. Want to apply this in medical diagnosis. Why is it that we need the idea of Bayes rule in medical diagnosis? We live in a stochastic environment where nothing is perfect. Okay? If somebody was tested and they realized that this guy has a disease, okay, because of the fact that the efficiency of machine is not 100%, okay, we can figure out what is the probability that the disease is present. It is not, machine is not going to tell us truth all the time. We see situation where somebody, do not have the disease and the machine says so. And we see situation where somebody have the disease, but the machine actually missed that. That is dangerous. Imagine if that disease is contagious. Okay, and that is the reason why the idea of the Bayes, need to be applied, because with the Bayes, that will give us an opportunity, to update whatever we believe. There's always going to be a belief. Okay, now let's take a look at this example. In screening for a certain disease, the probability that any person, wrongly get a positive result is 0.05. You can't read it out. 0.05 means 5% of the time when somebody is Eddie means there's no disease, the machine is going to say it's positive, which is the machine is not 100% efficient. Then the probability that a diseased person wrongly get a negative result is 0.002. Look at that. Okay? Then the overall rate of the disease in the population being screened is 1%. Okay? The overall rate of the disease is 1%. If you take a look at that 1%, that is looking like a prior. It's looking like a prior. Okay? Now, if my test now, okay, gives a positive result, okay, I submit myself, and they said, okay, I'm positive, then I want to figure out what is the probability that I do have the disease. Because there's possibility that I may not even have the disease, even when the machines say that I'm positive. Do you know the idea of the Bayes can be used to figure this out? I'm going to walk you through that right away. Okay, like I said, this is the general formula, the probability of belief. So there's a difference between this guy and this guy. So this guy is your database on belief. But why this guy is, you've already seen data, okay? And you now want to, you want to update your belief, with the data provided, okay? Now, I'm going to walk you through solving that problem now on the medical diagnosis. Now, if I want to use A and B, I can first start by saying, okay, I have a sample space. Of course, you know what I'm going to have in my sample space. The whole population will be partitioned into two. Those who have the disease and those who do not have the disease. So I'm going to start with I can call that B and B complement. Okay, that's my sample space. Okay, so I can write, let B represent disease. Okay, and B complement, no disease. Look at that. That's where you're going to start. Okay, now another possibility is testing positive and testing negative. So I can let A represent positive and A complement represent negative. Any question? Any question on that? You know, you need to first start by, with it, by this. You have to start by this. Okay? It's going to be so clear to you. Now, if I want to know how I'm going to position my formula now, then I need to look at the question. The question said, okay, if my test give a positive, okay, what is the probability that I actually have the disease? Okay, now give a positive, okay, A. You have A here, right? Now you want to figure out what is the probability that I have the disease. Do you see that? This is what you want to find. Is there anyone who doesn't understand how I formulate this? Because B stands for disease. I've already indicated that. And A, okay, stands for positive. Okay? And if you could look at the question, if my test gives a positive result, what is the probability that I actually have the disease? Now, the moment I have this, the next thing I'm going to do, by Bayes' rule, I'm going to reverse that. Take a look at it. I'm going to write the probability of A given B. Take a look at that. Then multiply by probability of B. Then this is going to be divided by probability of A. And you know what? Your probability of A here is going to be a total probability. So if I want to rewrite that, and then I'm going to rewrite that as the probability of B given A equal probability of A given B multiplied by probability of B. Okay, inside this, there's going to be this guy. I told you what you're going to have in the denominator of probability is more or less like totality. Okay, so what you have in the numerator is going to be part of it. So I'm going to write this. Or because I'm focusing on A, then the other one is going to be the complement of B. So I'm just going to write this. Any question? Any question on that? Like I said, do not hide your feelings. Okay? Do not hide your feelings. Ask question. If you don't understand, you're all good, right? Okay. Now, what I'm going to do now, I'm going to go back into the question. Okay? Let's look at the question. In the screening for certain disease, the probability that any person, which one is the any person? Okay, no disease, right? B complement. Okay, healthy person, okay, get a positive result. Okay, so B, this guy, and A. Do you see that now? So, and that is the reason why I'm going to have, so from my data now, because of my time, I got this equals 0.01. This is 0.99. This is 0.05. Okay. This is 0.002. Okay. What is this? 1 minus this. Now, let me show you what I've done. I'm going to show you what I've done. Because I need probability of B. Okay? The probability of, what is B? Disease. That will be the rate of the prevalence of that disease. And that is given to be 1%, right? You see that? That's a prior probability. Okay? So that would be 0.01, right? And the moment I know the probability of the disease automatically using the law of complement. This is going to be that because this guy will be 1 minus this. Do you remember the law of complement? Okay, that was how I got it. Okay, so maybe I'm actually going to say, P of this guy equal 1 minus that. Okay, using the law of complement. Now, the